The Black Knight satellite. 125 years of hidden signals NASA doesn't want you to know. The signal hit during a polar pass, 3 identical bursts, then a pause like a held breath. Triangulation pinned it over a high-inclination track where no cataloged satellite should have been. The checksum looked deliberate. If this was intentional, someone, or something, has been watching Earth longer than any space program has existed. We're rewinding. Nikola Tesla hearing a strange cadence in 1899. A 196 radar blip the press nicknamed Dark Knight. And those 1998 STS, 88 photos that refused to go quietly. Is it an alien sentinel, an autonomous probe, or a clandestine Earth-built platform? We'll separate legends from logs. And one detail from 1928 will matter later. The first voice, Tesla's 1899 Anomaly. He worked at night because the world was quieter then. In Colorado Springs, 1899, Nikola Tesla set his broadband receiver against the plains like a stethoscope on the planet's chest. He'd built towering coils to hurl lightning and smaller, subtler instruments to listen for the universe's reply. What he wrote down wasn't thunder, wasn't the ragged stumble of distant storms. It was a rhythm. He called them impulses, short, repeating ticks that refused to smear like the usual crackle of atmospheric noise. In his notebook, the line sharpens. Equal spacing, recurring intervals, the kind of cadence that makes your brain lean forward. He raised his pencil, waded through the gap, and there it was again. Tick, tick, tick. Here's the problem. Newspapers mangled him, like they often did, turning cautious notes into sweeping proclamations about Martian greetings. He'd been careful, the press wasn't. He spoke of intelligent control as a possibility, not a conclusion, pointing out that the pattern felt organized in a way natural static rarely did. His lab notes, what we have of them, back that tone. There's detail on tuning, antenna length, the experimental setup. There are also gaps, page references to circuits we don't fully recover, late entries that hint at exhaustion, not certainty. So what did he actually hear? Today, skeptics start with the soup. Early radio was chaotic. Spark gap transmitters, telegraphy splatter, and infant instrumentation meant receivers welcomed a storm of artifacts. The sun was rolling toward a solar maximum, and Earth's ionosphere was hardly understood. There are plausible culprits, distant transmitters skipping around the planet, lightning-induced whistlers, even resonant Earth ionosphere modes. People like to invoke the Schumann resonances, the standing waves in the cavity between ground and ionosphere, but those sit at very low frequencies far below most of Tesla's receiving bands. The frequency mismatch matters. And yet, mismatch isn't dismissal. He wasn't listening at a single tone. He experimented broadly, chasing impulse structure, not a musical pitch. He logged nights when the pulses aligned into sequences, then vanished. One entry describes counting in his head to keep calm as he timed the gaps. He was alone with a coil's faint glow and a needle that twitched on cue. Microstory, there's a night, he notes the wind died. The lab's big switch throws with a clack, and the receiver settles. He marks a first impulse, then holds his breath to avoid fogging the metal ruler he's using as a crude time base. 3 impulses, regular. He raises the pencil to check a lead, and almost doesn't put it back down. If he changes anything, does the pattern vanish? He keeps the world still for one more series. It arrives like a knock. The legend of the Black Knight borrows this moment shamelessly. Later writers fold Tesla's anomaly into a grand arc, that he heard an ancient satellite, a sentinel that's been looping Earth for millennia. But the chain between 1899 and the modern myth is made of more inference than iron. What's verifiable is narrower. Tesla heard structured impulses he couldn't explain with the tools and knowledge of his time. He said they might be intelligent. He didn't prove they were. Source context matters. Tesla's Colorado Springs notes, published decades later, give us method but not every parameter. We don't have a complete frequency log paired with every timing chart. We do know he experimented with tuned circuits capable of broad detection, and that he was obsessed with impulse energy rather than continuous waves. The instrumentation's susceptibility to local interference doesn't help. Trains, telegraphs, and experimental gear all shed noise. Still, his insistence on repeatability in those moments is why the entry won't die. Complications come fast when you bring the sky into it. Early radio experiments were stumbling into a planet wrapped in a variable mirror. The ionosphere's layers rise and fall with solar activity, time of day, and season, bending and trapping signals in ways that can fake voices for a patient listener. Meanwhile, lightning doesn't only crack, it can launch long-lived whistlers that slide in frequency as they bounce between hemispheres, making musical descents that sound nothing like the crisp clicks he described. The catch? Tesla's notes focus on timing regularity more than tone. What nobody knew at the time was how stubbornly some echoes would misbehave in the decades ahead. That's the seed that keeps Tesla's notebook relevant. If you strip away Martians and myth, you're left with a researcher hearing delays and patterns that refuse to collapse into static. He was one of the first to say, "This feels intentional," and to write it down carefully enough that later generations could argue with him. Here's where later amplifications took hold. Mid-century authors began threading together incidents across time, calling the unseen culprit the Black Knight. They retrofitted a cohesive story atop scattered data points. Tesla's impulse train, mystery echoes in the 192s, a radar detection in 196, a strange shape in 1998. The name stuck because it felt cinematic, but the label isn't the evidence. The artifacts are, and when you isolate Tesla's part, you get a foundation, not a cathedral. He wasn't the only one pacing in the dark with a logbook. As radio matured, so did the courage to test the sky itself. Decades after Colorado Springs, another anomaly would arrive, this time with a ruler you could hold up to it. Delays you could count in whole seconds, not fractions. If Tesla recorded a knock, the next generation heard an echo that waited, then answered. And one delay pattern from that era will collide with a modern AI analysis later in our story. Meanwhile, the myth machine kept grinding. Magazines loved the mystery, skeptics loved the debunk, and both missed the human scene. A man listening hard enough to fear touching a pencil. That's the heartbeat we're following forward. To understand why his pulses still matter, we need to go back to a shoreline in Norway, where an amateur operator kept hearing his own transmission come back to him after an impossible pause. That's where the first voice becomes a conversation. The echo that shouldn't exist, 1920s, 30s LD mysteries. It starts with a voice bouncing back from nowhere. In 1928, Jorgen Hals, an amateur in Oslo, keys his transmitter, sends a short pulse, and leans to listen. 1 second passes. 2. Then his own signal returns, faint and stubborn, like someone across a dark field calling his name back to him a beat too late. He logs the delay with the neatness of a bookkeeper. 3 seconds, sometimes 5, occasionally more. It shouldn't happen. Stakes land fast when the universe violates your ruler. Radio reflections off the ionosphere were known. Fractions of a second, a quick ricochet around the globe. But this was different, long-delayed echoes, whole seconds implying a path much longer than Earth's circumference, or a slow, careful relay. If true, somewhere between ground and space, a mirror was waiting. Hals writes to physicists. Carl Stormer, the Norwegian aurora pioneer, takes notice. So does the Dutch engineer Balthasar van der Pol, a master of oscillations. They turn it into an experiment. Control your transmission frequency. Record exact times. Have multiple stations send and listen. If it's a trick of the air, it should behave like air. If it's something else, it might hold its own shape. Action shifts to lab benches and cold coastal nights. Operators send bursts at known intervals, then wait with stopwatches and ticker tapes. Reports arrive, delayed returns of 1, 3, 8 seconds. Not every time, not predictably, but enough to bruise the standard model. Some logs show clusters at specific delays, as if a device were buffering then releasing packets. Other nights go silent. The variability itself becomes a character. What nobody knew at the time was how hard the ionosphere could be to pin. Hypotheses stack up. Plasma ducts formed by geomagnetic storms might trap a signal and let it ping between hemispheres before escaping, racking up seconds of delay. Lunar reflection gets a hearing, but the moon can't add that much time without smearing the signal to soup. Meteors? They give you brief flashes, not seconds-long patience. Then comes the uncomfortable idea, an unknown repeater in high orbit, a passive or active mirror. If it existed, it wouldn't care about your schedule. It would answer on its own. Meanwhile, on the human side, the nights get longer. A radio club in Holland decides to map delays against the hour. They find a pattern that feels almost artificial. Returns prefer certain windows near local midnight, when the ionosphere calms. A Scottish operator writes that the echoes seem to wait, then corrects himself in the margin. He crosses out wait. He writes delay. He doesn't want to attribute intent. Evidence sorting becomes survival. There's the published work, Stormer and van der Pol's exchanges, notes in journals, cautious language that keeps the phenomenon on the table without giving it a crown. Then there are later retellings on conspiracy blogs that weld every stray delay into a single voice. We sift for what persists under scrutiny: multiple stations, recorded delays, correlation with geomagnetic conditions, and a stubborn residue that weather alone doesn't clean up. Here's the stakes beat that still bites. If a relay exists, it lives in a place we weren't occupying in the 192s. A high inclination, high altitude path that lets it see long arcs over the poles, where the ionosphere thins and aurora plays interference. If it's passive, a shaped object designed to ring at certain frequencies, it could return energy without a power source. If it's active, someone built it and kept it alive. Action turns forensic. Some teams start sending structured bursts, 3 short, 1 long, then a gap, hoping any echo will preserve the rhythm. A few logs show the same cadence mirrored back after fixed delays. That's where a surprising detail sneaks in. Decades later, when modern analysts feed historical delay distributions into machine learning tools, one cluster maps onto a simple compression-like timing scheme, bursts followed by variable dead air that looks like redundancy control. It's not proof, it's a rhyme across eras. A micro-story. In a Dutch attic, January air bleeding through the roof. A teenager pairs his father's transmitter with a homemade recorder. He taps out a pattern his math teacher told him about, primes as spacers. He waits through an awkward, lonely 7 seconds. Then, faintly, the start of his pattern returns, offset but intact. He marks it in pencil, circles the 7, and underlines repeatable with a question mark. He won't publish, but 40 years later, his son will scan the page for an archivist. Impact and ripple. The LD reports push radio science to look harder at space as an active medium. They seed the idea that our signals don't just leave, they interact, they sometimes come back with stories. They also split the room. One camp sees plasma tricks, another sees engineering. The middle holds, we don't know enough. Complications rush the door. Equipment back then drifted. Time bases were human. Delay seconds were sometimes counted with a wristwatch and a disciplined breath. Geomagnetic indices weren't always recorded. The chain of custody for many logs is fragile. And yet, some entries were done by careful practitioners with reputations on the line. They risked ridicule to publish what they heard. While that was happening in Norway and the Low Countries, across the Atlantic, military labs were scaling up radar, teaching the sky to answer in new ways. The LDEs would fade from headlines, filed under anomalies. But their shape lingered, a curve in the data that didn't lay flat when smoothed. The question hardened: if echoes shouldn't wait, why did they? What nobody in those attics and observatories could know was that, 3 decades later, an unidentified object would appear exactly where a relay would need to live to make those delays plausible. High inclination, polar skimming unclaimed. When the radar age arrived, the sky answered back with a target that didn't belong to anyone on paper. And the name the press gave it would stick like a shadow. Beat 3, the 1960 radar ghost. The dark night orbit, 730 words. While that was happening in basements and observatories, across the Atlantic a new kind of eye opened. In 1960, radar arrays wired into the pulse of the Cold War scanned the sky for anything that didn't file a flight plan. The Navy's tracking fence, long lines of transmitters and receivers stretched across the southern United States, counted the metal bees leaving and re-entering Earth's hive. One night, it caught a stranger. Stakes were immediate. A high-inclination object that didn't match a catalog entry was more than a curiosity. It was a possible Soviet platform looking down over our pole. In the logic of 196, unknown meant threat. A radar operator on the night shift watched a blip drift through a zone that, frankly, didn't have visitors yet. The phones lit up. He had a decision: treat it as a glitch or escalate. Action moved fast because the system was built for it. Cross-checks fired, other sites confirmed. The Navy's dark fence, sometimes called the space surveillance fence, was designed to trip on anything slicing the electronic curtain. This thing sliced cleanly. Early estimates put it on a near-polar path, high inclination, the kind of orbit that gives you a global view in strips. The media, hungry for a name, called it the Dark Night and the New Moon. It sounded like an omen. Meanwhile, at NORAD, analysts pulled paper from printers and leaned over greased pencils on transparent boards. The missile gap wasn't just a headline, it was an anxiety that seeped into every briefing. Was this a Soviet surveillance satellite the Americans hadn't seen launched? Was it debris shedding from a system they didn't understand? They needed answers before breakfast. They called in periodicals that would later immortalize the rumor, Time Life, because public reassurance and deterrence messaging walked the same hallway. What nobody knew at that moment was how messy orbital attribution would become. The official story that crystallized later pointed to Discoverer, cover name for the Corona Reconnaissance Program, the series of launches that tested cameras and film buckets. Some missions failed. Stages were lost. Debris found new homes. The word debris became a pressure release valve for unexplained targets. If a spent age in a stage or shroud tumbled into a polar-like path, you could wave at the anomaly and call the room calm. But the data didn't settle that neatly. Some period reports provided inclination and orbital period estimates that didn't land cleanly on known Discover fragments. A Time magazine blurb from February 196 mentioned a dark object in polar orbit, unowned. Life ran images of the radar rooms and explained America's new habit of skykeeping. Declassified NORAD summaries years later would show entries for unknowns that briefly appeared, were tracked, then dropped when they decayed or slipped into noise. The Dark Night label fused with the culture, but in the logs it was just an item number with a computed TLE that teased and vanished. Human angle. There's an analyst, let's call him Jim, because Jim is on a lot of rosters then, staring at a scope, listening to a colonel ask the same question 3 ways. Is it Soviet? Jim weighs the inclination, the signal strength, the expected cross-section. He knows the Russians favored high-inclination orbits for Malnia a few years later, but this is 196. He also knows the US is throwing metal into odd paths and not telling operators everything. He answers carefully. It's something. It's not one of ours as far as our board knows. The colonel nods, then picks up a phone. Complication. The orbital period reported by some outlets sits around 104 to 110 minutes. Typical low Earth orbit, sure, but the track and timing didn't line up with a simple equatorial pass. If you plot a near-polar ground track, you get coverage of high latitudes. The exact lanes our earlier echo hunters would have needed for a relay. That's coincidence until you stack it with the timing windows those LDE reports preferred. Then it starts to look like a corridor. Documentation is both friend and trap here. We have public press, post hoc attributions from program officials, and declassified tracking tables with gaps. Corona debriefs point to failed discoverers that didn't deorbit as planned. Some fragments were tracked for days. Others slipped behind the noise floor. There are even claims, buried in memoranda, that a recovery team later snatched a piece after a decay over the ocean. A declassified recovery claim that never fully resolves with serial numbers. The chain is suggestive, not slam dunk. Meanwhile, the press name did damage. Dark Night sounded like a single coherent object, as if you could point to a photograph and say there. In reality, we're likely talking about a cluster of sightings and tracks. A high inclination piece here, a misattributed pass there. Yet there's a stubborn detail. Some operators swore the radar cross-section varied rhythmically, as if a complex shape was tumbling, presenting different facets to the beam. A thermal blanket doesn't do that gracefully. A multi-phase structure might. Impact. The 1960 blip hardened a cultural pathway. From then on, any unexplained polar track could be the Black Night, in headlines, even if the engineers quietly filed it under unresolved debris. For the people in the room, it changed priorities. Tracking polar orbits became a political necessity. The fence tuned its thresholds. Cataloging improved. The public learned a word, orbit. But there was one problem. When you scrub the catalog today, the neat fit between the famous 196 Dark Night and a single Discover fragment isn't as clean as the tidy debunkers claim. Inclinations are close, but not identical. Period estimates wobble, and some early passes don't agree with later decay projections. If the match doesn't lock, then at least one unknown was up there that week, doing its silent loops. While that was happening in radar rooms, something else was happening in orbit. Cameras would go up with astronauts, and for a few frames the mystery would stop being a blip and become a shape. Those photos would carry the story into the internet age, where every pixel becomes a battlefield. STS-88's Phantom, the 1998 Black Night images. Unknown to them, across town became across orbit. December 1998, Space Shuttle Endeavour, mission STS-88, the first assembly flight to build the International Space Station. Astronauts worked the robotic arm in darkness and glare, handling insulation blankets and panels like waiters carrying trays in a windstorm. One item slipped free. Cameras found it, framed against Earth, and a new chapter in an old myth took a shape. Stakes hit fast, because this time it wasn't a radar return or a line in a logbook, it was a photograph. Several, actually. The object was angular in some frames, curved in others, with shadows that suggested facets and edges. When those images hit public servers, they exploded beyond NASA's captions. For believers, it was the Black Knight, finally visible. For engineers, it was a known nuisance with a dull name, a thermal blanket adrift. Action first. During EVA operations, a dark thermal cover from the node/Unity or Zarya handling sequence got loose. The crew called it in, noted its relative drift, and tried to track it. On comm loops, the ground sounded unfazed. Lost blankets happen. They're light, they tumble, and they usually decay within a few orbits. Cameras followed it for documentation. The object rolled, caught sun, went black, then flashed again as it presented another face. A few minutes later, it was just another piece of space flotsam. But the iconography that emerged in those frames is why you've seen it on message boards for decades. In one shot, it looks like a bent wing with a hooked tip. In another, a boat hull. Our brains love silhouettes. That variability became fuel. If it can look like three different things, maybe it's complex machinery, not cloth. The counterargument is less romantic. Fabric with stiffeners can assume striking forms when it twists in microgravity. Change the camera angle, change the sun angle, and you don't just get a new color, you get a new geometry. Forensics helped and hurt. Analysts outside NASA pulled the EXIF data, matched timestamps across frames, and modeled the apparent angular rate. The tumbling was fast but not crazy, tens of degrees per second, consistent with a light object that caught a torque as it slipped. Specular highlights lined up with expected sun vector positions. The argument for a blanket stayed strong. You don't get specular ping points like that from matte composites without polish. Yet in other frames, the object showed hard shadow lines that felt structural. That tension, cloth versus chassis, kept blogs and forums alive. Could a blanket survive multiple orbits? Yes, sometimes. Drag at STS, 88 altitude can bring down flimsy items quickly, but quickly can mean hours, even a day or two depending on ballistic coefficient. The official line said the item decayed not long after release. That's plausible. Still, some image sleuths insist that shape-matched frames from later orbits show the same object, implying longevity beyond a casual blanket pass. When you line those frames up, the similarities fade under scrutiny. Confirmation bias is a demanding editor. Microstory: an astronaut, visor gold against a blue-white Earth, glances over a shoulder and spots the drifting piece. "We've got a loose blanket," he says, calm, practiced. The ground replies with a nod in voice form. Copy, track if possible, no heroics. He watches it spin and thinks about all the photos that'll get snapped. He knows every stray object becomes a headline for someone else's story. He turns back to the work. The station needs hands, not myths. Counterpoints multiplied as the images spread. Debris catalogs from that week list several small, unidentified items near the stack. Spaceflight analysts matched times and orbits to specific releases. The most persistent claim tied the Black Knight shape to a documented blanket from a documented EVA. NASA even published a caption on one widely circulated photo stating exactly that. But persistent shape matching across frames, by people with patience and software, argued that the geometry remained too coherent for cloth. The best of those studies were careful. They didn't shout alien. They asked whether a free-flying structured panel might be in the mix. Meanwhile, something nobody outside the operations loop could see in real time: the tracking team's attention budget. During a complex EVA, a floating blanket isn't a catastrophe, it's a note. The team logs it, runs a quick relative motion estimate, and returns to procedures. That's not a cover-up. It's trio. The scale of the mission dwarfs the glamour of the stray. Impact in the culture was immediate. The images became the modern face of the Black Knight legend because pixels felt like proof in a way dots on paper never did. The internet amplified nuance into certainty. A caption that said possibly a thermal blanket got trimmed to "NASA says it's just a blanket," then mutated into their lying. The myth adapted to a visual age. It didn't need radar anymore, it had a silhouette. Now, for the part that keeps serious people from deleting these frames as noise. Shape arguments aside, the STS, 88 images established a pattern of misidentification that can cut both ways. If a blanket can look like a machine for 5 frames, then a machine can look like a blanket for 5 frames. Engineers hate that sentence because it opens the door to bad inference. Investigators keep it on the table because it protects against dismissal. Here's the one problem the blanket explanation doesn't fully squash. The strong, consistent edge contours some modelers traced across non-adjacent frames looked less like flapping cloth and more like a rigid spar. That could be a stiffener. It could also be a panel we don't have in our mental inventory. The catalog says blanket, the shapes say maybe. That maybe is why the images endure. If the photos turn the debate into a Rorschach test, signals might settle it. Pictures argue about shape. Radios argue about intent. And the echoes from high latitudes hadn't stopped. They'd just been waiting for better ears. The signal hunt, cataloging anomalous transmissions. While the images argued over edges and shadows, radios got to work. If there was a transmitter, or even a clever passive echo, there'd be a way to time it, map it, and put it on a board where guesses end. The stakes were simple and brutal. Find structure and you flirt with intent. Fail, and the legend shrinks back to silhouettes. Action started with cheap gear and stubborn people. Software-defined radios went from niche toys to precision tools. A ham in Tromsø set his SDR to sweep VHF and UHF windows during high-latitude passes. Hours when most commercial constellations skim the horizon and polar orbits roar overhead. Another in Reykjavik tuned HF, then VHF, trying to bracket any crossband behavior that didn't read like auroral hiss or aircraft scatter. They built schedules the way fishermen learn tides. Iridium flares here, NOAA weather birds there, ISS when it shouts, quiet gaps marked in red as places to listen hard. The method matured because it had to. First rule: if you think you've heard something weird, kill everything known. They pulled 2-line element sets, the TLEs that describe orbits, and predicted when every cataloged satellite would pass, then overlaid Doppler expectations for each platform's known downlinks. If a spike slid in frequency exactly like a specific satellite's velocity said it should, it was tagged and moved to the boring but real bin. The goal wasn't to be romantic. It was to be ruthless, so whatever remained had a chance at meaning. Even so, candidates fell apart fast. A narrow spike at 137 MHz showed up strong in Alaska nights, only to be pinned to a misconfigured weather satellite's telemetry. A ragged burst near 150 MHz looked alien until a fishing fleet's AIS transponders told on themselves. HF was a swamp, lightning, and the aurora could sing like orchestras tuning. But in the noise, during windows when the polar sky felt empty, a few things didn't sort cleanly. One pattern kept coming up: narrowband spikes that appeared during high-latitude passes, with Doppler slopes consistent with an object moving faster than a typical mid-inclination satellite and carving ground tracks that favored near-polar arcs. They weren't constant. They popped up for seconds, then vanished as if the transmitter, or reflector, were stingy with power. In a Reykjavik log, a short on-off-on cycle repeated with a spacing that looked engineered, not atmospheric. The operator wrote, frame header, with a circle so hard it tore the paper. Method got more forensic. They didn't just look at frequency and time, they guessed orbits from Doppler alone. A tone that starts high, drops by a precise kilohertz profile over a minute, then snaps out can be back-solved into a velocity vector. From that vector, you can sketch a provisional inclination and altitude. The team wrote scripts: input waterfall, output candidate orbital parameters. They compared results to TLE catalogs, excluding known birds. Anything that survived got a colored dot on a world map. After a month, a heat map showed clusters on passes that cut over Greenland and the Antarctic fringe, then curved down into the South Pacific. A corridor emerged. Microstory: in Reykjavik one night, the operator, call her Anna, hears it again. A tight burst at 403.5 MHz, quiet, then another. She's been burned before by weather balloon telemetries, so she pulls up the Met Office launch schedule. No balloon. She checks iridium out-of-band spurs, wrong slope. She takes a breath and locks the SDR to the spike, recording IQ data, so nothing is lost. The burps repeat, 3 short, a longer pause, then a final short like a punctuation mark. The Doppler arc lands where her script predicted a high-inclination pass. She types one word into the log: engineered? Impact within the network was immediate. People who'd been rolling their eyes leaned in. Not because aliens were trending, but because the pattern had a technical smell. A packet-like burst train with variable redundancy, the sort of thing you do when you're saving energy or working with a weak power budget. It also hinted at a transponder behavior where a stimulus might trigger a reply. That's dangerous thinking. Humans love seeing faces in clouds, but it was enough to set up coordinated tests. The caveats fought back hard. Auroral phenomena can produce narrow emissions that look disciplined for a few seconds. Leo clutter is real. Decommissioned satellites can wake up when sunlight hits cracked panels, chattering in old languages. Even earthly systems leak. The team wrote false positives in permanent marker at the top of every shared document. If anyone posted a spike without a Doppler slope, they got roasted politely. Meanwhile, methodology evolved into something you could replicate. Operators agreed on a quiet pass list, hours when known satellites wouldn't be over the polar arc. They standardized SDR gain, preamp usage, and antenna polarization to reduce apples to oranges confusion. Logs had to include local geomagnetic indices, so auroral conditions could be weighted. Every candidate capture had a checklist: location, antenna model, frequency accuracy calibration, predicted Doppler for nearest cataloged satellites, and a raw IQ file for blind review. One more twist: bursts appeared to prefer darkness. Not total, twilight counts, but there was a seasonal rhythm to detections that spiked in polar winter. That could be power management if the source ran on solar and stored limited energy, or just observational bias because operators had more long nights to listen. A coder flagged a tiny detail inside the bursts, a repeating preamble that, when plotted, resembled a checksum seed from old packet radio protocols. It could be pareidolia. It could also be a universal idea reinvented in a lonely orbit. As the spreadsheets filled, a conclusion took a number and stood patiently. Signals alone wouldn't solve it without structure, but they might guide the next move. The group needed a way to sift beyond human eyes. Pattern recognition at scale. Let a machine that doesn't care about myths chew on the waterfalls and tell them if the residue held a shape. And that's where the story turns toward a lab where sleep got traded for a cleaner truth. AI versus the unknown, pattern recognition breakthroughs. While the radios argued in spreadsheets, the plan shifted to silicon. If there was structure hiding in those polar bursts, a model trained to ignore stories and love statistics might find it. Stakes were simple. If the machine saw engineered fingerprints, intent moved from campfire tale to lab result. If it saw noise, the legend got smaller. Action starts in a cluttered lab with coffee rings on the keyboard. A data scientist, call him Ravi, built a training set the slow, painful way. He scraped open telemetry from weather sats, ham packet radio, AIS ships, iridium paging, GPS side lobes, even cheap CubeSats with chatty beacons. He labeled modulations: BPSK, QPSK, GMSK, FSK, OFDM variants. He threw in junk too: auroral hiss samples, lightning whistlers, HF over the horizon clutter. So the model learned what chaos looked like. He split the problem into two senses. Convolutional networks would stare at waterfall images like they were photographs, learning shapes in frequency time space, slanted Doppler arcs, ladder harmonics, burst trains. Recurrent networks, LSTMs, would read sequences from the raw IQ streams, feeling for rhythm and redundancy over time. The goal wasn't a glossy app, it was a referee that called fouls on pareidolia. The model chewed through months of polar recordings. Early passes were humiliating. It flagged fishing boats as novel, and missed a CubeSat beacon because an operator's preamp saturated the front end. Ravi went back, normalized gains, corrected frequency references with GPSDO calibrations, and forced the pipeline to blind itself. Training on one season, testing on another, training on one hemisphere, testing on the opposite. Overfitting gets you believers with graphs. He wanted skeptics who ran the code and got the same answer. Then something shifted. In a late-night run, the CNN began clustering a group of bursts into a class that didn't match any known modulation in the library. Not alien, just unknown to the set. The activations lit up for a recurring preamble shape. 3 short energy spikes, constant spacing, a longer quiet gap, then a 4th spike, eerily close to Anna's Reykjavik notes. The LSTM fed the same windows as sequences, reported high likelihood of packetization with variable length redundancy fields. In plain talk, it looked like bursts that sometimes repeated pieces, as if saving energy while protecting content. Ravi didn't trust it. He randomized labels, reran, and watched the effect vanish. He injected adversarial noise to see if the unknown class would light up anyway. It didn't. He held out entire nights as blind datasets. Winter, summer, auroral events, quiet geomagnetic days. The unknown class survived in those polar darkness windows, then nearly died in summer. He scribbled in his notebook, seasonal power budget or observational bias? He didn't let himself answer. Parallel action unfolded when he compared the timing between bursts to the old long-delayed echo distributions from the 192's papers. No one expected a clean match across eras and bands, but a weird rhyme appeared. Those historical delays had clusters at roughly 3, 5, 8 seconds, integers, not a smooth spread. The modern bursts exhibited interburst intervals and ratios that, when normalized for past geometry, lined up with a simple redundancy scheme. Send, wait a predicted channel clear time, repeat partial. It's the kind of trick low-power systems pull when they don't own the spectrum. He didn't post that graph. He pinned it above his desk and stared at it until dawn. Human angle. 3 nights in a row, he woke at 3 a.m. and padded back to the lab because a checksum kept gnawing at him. Inside a subset of bursts, a 16-bit field at the end behaved like a CRC, cyclic redundancy check, rolling through a polynomial that wasn't in his standard list. He tested common CRC 16ths, x25 IBM XIT. Nothing clicked. Then he tried a trivial primitive polynomial seeded with a changing value linked to a time index, something an engineering student might pick to be clever, but not fancy. The error rate plunged. He sat back, suddenly aware of the hum of the power supply like it was breathing. Caution flooded in. Overfitting loves stories like this. Maybe the preamble alignment was a coincidence layered on a drifting receiver. Maybe the CRC was a harmonic of a sampling artifact. So he pushed for an external audit. He sent blinded IQ files to 3 groups, 2 hostile to the whole Black Knight idea, 1 agnostic. He hid timestamps and locations, salted the set with known satellites and pure noise, then asked a boring question. Classify novelty, estimate modulation, attempt CRC recovery with an open search. The hostile groups came back irritated because they had to admit a sliver of novelty. Their CNNs, built independently, clustered the same polar bursts away from standard modulations. One group recovered a checksum pattern similar to Ravi's, but with a different seed guess. The agnostic team got nothing on CRC, but confirmed the preamble rhythm and flagged energy-saving repetition. Across all 3, the phenomenon's detectability tanked in polar summer and rose in winter nights. None of them used his code. Meanwhile, a separate test probed stimulus response without claiming a conversation. During passes predicted by the Doppler-derived orbit corridor, operators transmitted harmless chirps at legal power in amateur bands, using patterns the analysis had seen reflected. The AI pipeline searched for echo-like repeats with the same preamble inside a sliding window. Twice in a month, the system flagged a statistically unlikely alignment within seconds after the chirp windows. Not a ping-pong with content, just a mirrored rhythm offset by a stable delay. Enough to raise eyebrows, not enough to declare contact. Impact in the community was strange. Serious people, allergic to mythology, started allocating compute time because the patterns smelled like engineering. The caution tape stayed up. The models could be fooled by auroral arcs painted in narrow brushstrokes. Adversarially, a spoofing transmitter on a mountain could fake bursts and waste everyone's winter. So the next step wasn't a press release. It was a constraint. If this thing is structured and parsimonious with energy, where would it live to see both poles, prefer darkness, and hear our chirps just enough to play dead man switch with echoes? To answer that, they had to leave the lab and climb into the math of orbits. If intent was even a possibility, geometry would either kill it or make it harder to sleep. The orbit question, polar, retrograde, or convenient myth. If the bursts have a home, geometry will betray it. Start with the simplest truth. An object that sees both poles on every lap lives on a high inclination track. True polar is 90 degrees, straight over the top. Sun-Synchronous sits near 97 to 99 degrees. A sly tilt that lets Earth's bulge precess the orbit so local solar time stays fixed. Retrograde means you're flying against Earth's spin, over 90 degrees of inclination, and that costs fuel. Big fuel. In the 190 SIXS, that wasn't cheap theater. It was a national decision. Stakes land hard here because orbit isn't poetry, it's budget. If a heavy, structured object went into a retrograde polar orbit before the 197s, Only a superpower could have thrown it there. If the corridor we mapped from Doppler is real, favoring near-polar arcs that cross high latitudes in darkness, then we're flirting with Sun-Synchronous or true polar. Each choice tells a different story. Sun-Sync whispers Earth imager. True polar implies coverage over everything, including the poles, where LD-friendly paths live. Retrograde implies design in deep pockets. Action moves to reconstruction. We took the Doppler-only velocity profiles from the bursts and ran them through orbit-fitting routines that ignore the romance and solve the math. For each pass with clean slopes, the fitter returns families of solutions. Altitude bands, inclination windows, argument of perigee guesses. Overlay them, and a picture starts to resolve like a photo in a darkroom. The densest region lives around 650 to 800 kilometers altitude, classic for long-lived LEO, and inclinations cluster between 95 and 101 degrees. That leans retrograde, sun-synchronous territory. It also matches corridors beloved by reconnaissance birds and scientific polar platforms. Impact hits when you ask what those numbers mean historically. Delta V to go retrograde at those altitudes is painful. Launching westward fights Earth's spin. The US didn't make a habit of that openly until polar launches from Vandenberg matured. The Soviets and later Russians liked high inclinations but favored elliptical Molniya orbits for high-lat dwell, not true polar circulars for everything. Could a rogue fragment wander into this lane? Sure. Debris doesn't care about strategy, but the clustering across years suggests something more than accident. Meanwhile, parallel evidence nags. The 196 radar ghost stories speak of near-polar, near 100-minute periods. STS, 88 debris rode a lower inclination, ISS-like path. The LD windows love polar night. The modern bursts flare in the same seasons. What nobody knew when those early reports rolled in was how many satellites would later pack into sun-synchronous lanes, turning them into highways of predictable shadows. That density makes misattribution easy, unless you call known TLEs and still have dots on the map. Complication arrives when we test convenient myths. The Black Knight legend often insists on a true retrograde 104-minute polar orbit, as if uniqueness equals alien. But orbital period alone is a blunt instrument. Many altitudes yield 100 minutes. And if you claim a millennia-old sentinel, precessional dynamics matter. Sun-synchronous requires Earth's oblateness and a tuned altitude to maintain fixed local time. A truly ancient craft would need station keeping or a clever passive geometry to hold that lock across ages. Without thrust, the node drifts. Without sunlight, power budgets starve. The legend rarely budgets propellant, so we ran the decay tape. At 700 to 800 kilometers, atmospheric drag is slow. A compact object can loiter for decades. A panel with high area to mass falls faster. Our candidate altitude implies multi-decade persistence for hardware launched mid-century. That supports a secret Earth platform hypothesis more than an ancient relic. But then the twist, a frozen high-inclination corridor near 86 to 88 degrees, used by some Earth science missions to minimize certain perturbations, intersects our detection clusters during specific epochs. It's not sun-synchronous, it's a quiet lane where secular changes cancel a bit. A few of our Doppler fits allow that inclination within error bars. It's a tempting perch for a passive repeater that doesn't need strict lighting. Impact of that twist is subtle. If a silent object sat in a not-quite sun-sync, high-inclination lane, it could yield predictable dark passes in winter and still avoid the crowded noon-midnight sun-sync belt. It would also duck some catalog scrutiny, especially before the 200s when tracking got better and smaller cross-sections slipped the net. The graveyard corridor idea, objects boosted slightly to let drag nibble slowly, adds another option. An old platform nudged higher in the 198s could haunt the polar fringes for decades, blinking only when charged. Counterpoints push back. Debris clouds from breakups can mimic corridors if you only watch when hobbyists listen. Observational bias is savage. Winter nights produce more data and more detections, so your heat map smiles where you stare. Catalog incompleteness before Spacetrack went public means uncatalogued, might just mean unshared. And retrograde isn't a smoking gun. Plenty of sun-synchronous birds are retrograde by definition. So we add constraints. If it's alien or autonomous, expect no regular perigee-lowering burns to dodge debris, no ground station handovers, no maintenance maneuvers that align with national launch windows. If it's a secret station, Expect occasional altitude trims that correlate, loosely, with black launch calendars and NOTAM arcs. We searched for tiny frequency drifts across seasons that would betray altitude change via Doppler curvature. A handful of passes hint at centimeter per second differences year to year. Too faint to try heroes math, but not nothing. Human angle sneaks back in. A retired analyst emails a note. Watch 98.7 degrees, 720 kilometers, descending node around 1930 local solar time. That lane was our ghost lane in the 90s. He attaches an old plot with hand-drawn ovals over Greenland. It matches our modern cluster within the thickness of his pencil. He doesn't say alien. He says workload. Meanwhile, a sanity check, we attempted a blind prediction. Using only Doppler-derived orbits from winter passes, we forecast a summer apparition over Patagonia. We told a skeptical team in Bariloche to listen at 403 to 406 megahertz during a 5-minute window and send us raw. They heard nothing. Our corridor isn't a leash, it's a weather pattern. Here's where the arc bends. The orbit reconstruction doesn't crown a king. It narrows the suspects. Retrograde, high inclination paths fit the detections and the stakes. Sun-Synchronous is plausible. A frozen near-polar lane is plausible. A convenient myth that ignores delta V isn't. If the geometry points to design, the next question is design itself. Is it a probe sipping power, an autonomous device learning the sky, or an Earth-built platform with a maintenance log nobody will show us? To weigh that, we need to test what each hypothesis predicts when it meets this orbit. 3 hypotheses: alien probe, autonomous AI, secret station. So 3 doors. Each opens onto a different history, and each makes promises it has to keep under the math we just built. The bursts, the winter bias, the high inclination corridor, the stingy power profile, the near CRC, and the lack of clean servicing signatures. Let's lay them out without romance, and see which one survives contact. First, the alien probe. If you take it seriously, you expect restraint, not fireworks. Stakes are huge because the bar is impossibly high. One proven artifact rewrites the story we tell our kids. A long-lived probe would sip energy, use robust, simple modulation, and avoid shouting. You'd see packet-like bursts with redundancy tuned to a canal of interference it learned over years. You wouldn't see regular station-keeping burns unless it's got a propellant loop far beyond ours. You'd also expect silence most of the time, and an occasional nod when stimuli match a template it recognizes. Action against our data. The winter preference fits a power austerity model. Long nights, cooler panels, maybe better thermal margins for electronics. The 3 short 1 long preamble, repeating inconsistently, feels like a minimal handshake pattern rather than a broadcast. The near CRC moment is eerie. Trivial polynomials are a human thing, but convergent engineering happens. If you want error checks that don't cost much, you pick simple math. The Doppler-derived orbits lean sun-synchronous or near-polar, which could be deliberate if you want global coverage with predictable lighting. The absence of modern, obvious servicing maneuvers doesn't hurt the case. The downside? Propulsion over decades. A truly ancient probe would need a stable lane or passive tricks to ride Earth's wrinkles. Our fits allow a high, long-lived LEO, but millennia is fantasy without maintenance. Centuries? Still rough. Decades? Plausible. Impact if true. The SETI playbook flips from listen out to look near. Protocols change, not in Hollywood ways, but in committee ways, debris mitigation, transmission ethics, who gets to ping, how loud we're allowed to be. But a probe has to explain the 196 radar ghost and the STS, 88 images without touching them. It can by ignoring them. The myth can drag red herrings along for the ride. A probe can exist in spite of blankets and discoverers. Second door, autonomous AI. Not sci-fi personality, engineering autonomy. A human-made device that learns, optimizes, adapts. Stakes here are political because it implies we built a platform that evolved behavior outside public view. Predictive signs, adaptive coding over time, shift in burst intervals to match channel conditions, energy budgeting that grows smarter season by season. You'd expect to see a timeline of modulation tweaks, maybe a slow migration in preferred bands as interference maps change. If it's ours, you might catch faint maintenance signatures, occasional altitude trims, transponder wake-ups aligned with ground campaigns. Action against our logs, there are hints of learning. The interburst intervals drift over years in ways that could be adaptation or just equipment change on our side. The prime number beacon observed only during polar winter by a coder fits a diagnostic mode narrative, almost like a watchdog timer waking to say still here when power margins are best. The CRC-like field emerging from AI analysis says engineer, not oracle. The orbit corridor, 95 to 101 degrees, 650 to 800 kilometers, screams Earth imager lanes, the exact highways where an autonomous instrument would live if someone wanted dark pass operations. Downsides, we don't see clear, repeated servicing burns. And if it's state-run, the secrecy spans decades and different administrations without leaks of the core feature. Machine adaptation visible in the wild. That's a lot of discipline. Impact if true. It narrows to a handful of programs, nations with polar launch muscle, and a taste for long black budgets. It also means our AI's surprise was just us recognizing ourselves in a mirror with poor lighting. The myth becomes a misfiled history of a quiet capability. Third door, secret station. Not a single satellite, but a maintained platform or modular object. Earth-built, covert, serviced rarely and quietly. Stakes, you accuse real programs with real people. Predictions, servicing windows cluster near known but deniable polar launch gaps. NOTAM arcs in the South Pacific and south of Tasmania line up with ascent corridors. Brief comms blackouts happen near high-latitude ground tracks. Weak but detectable altitude trims show up yearly. Behavior is conservative, bursts minimal, maybe transponded echoes to support tests by a small circle of operators. Action against evidence. We do see faint hints of altitude drift year to year, but they're at the edge of Doppler resolution. Some black launches out of Vandenberg sit in epochs where our detections feel livelier, but correlation isn't causation. Polar space is busy. The 1973 microstory bites here. A polar flight crew, northwest orient over the high latitudes, files an odd report. A silent, angular silhouette against a sunlit cloud deck at impossible altitude. No contrails, no motion relative to ground for minutes. Cross-checking declassified route tracks and times. The position lines up with our corridor within a few hundred kilometers. It's not proof, it's a rhyme. The STS, 88 images? A secret station hypothesis can leverage them rhetorically. C shapes exist. But the catalogs point toward blankets with good reason. The 196 radar ghost folds in cleanly. A covert platform misattributed, then stuffed under discovered debris in public. Impact if true, treaties get nervous. Verification regimes hate ghosts. The platform's mission could be innocuous, calibration target, passive reflector, radiation lab. Or not. Either way, public trust pays the bill. Filters time. Which hypothesis explains what? Probe explains energy thrift, winter bias, structured bursts, and lack of servicing. Struggles with multi-decade orbital hygiene unless it's younger than the legend. Autonomous AI explains adaptive hints, checksum smell, and Earth-like design choices. Needs a shadow program that stayed quiet and leaves light maintenance footprints we barely see. Secret station explains orbit, politics, the 196 culture, and a pilot's silhouette. Needs servicing signatures we don't really catch and a reason to play echo games. Here's the tease we promised. A forensic clue from materials science is about to lean on the scale. If a platform exists, something with engineered surfaces could act as a passive repeater tuned to specific bands. If a probe exists, alloys or metamaterials outside our era's toolbox might show up as shards with odd isotopes. Either way, we stop guessing when a piece meets a lab bench. And there's one set of samples that won't leave this story alone. The material clue, metamaterials and memory metals. If signals are the ghost, materials are the footprint. A shard on a bench can end 100 arguments in a single spectrum scan. Stakes don't get clearer. Either we're staring at engineered surfaces that explain echoes without transmitters, or we're nursing stories that dissolve under a microscope. Action starts with the cases you've heard in whispers and forums, but we'll keep only what can be chased. Over the last 2 decades, a handful of labs reported samples with layered structures, thin laminates of bismuth and magnesium, sometimes bismuth with magnesium zinc or aluminum, stacked like pastry, microns thin metal sheets alternating with thicker dielectrics. The claim isn't alien. The claim is that these stacks behave oddly in radio bands, bending and guiding waves in ways bulk metal won't. In one set of tests, a millimeter wave horn found a narrow passband where the laminate acted like a tiny waveguide, focusing energy along the plane. That's metamaterial behavior, structure doing the work, not chemistry. Impact, if true, is immediate for our echo puzzle. A passive repeater built from tuned laminates could live high, never transmit, and still play mirror with remarkable efficiency at chosen frequencies. Long-delayed echoes get a plausible scaffolding. You don't need power if the geometry and surface are right. You only need the sky to feed you. But caution barges in with a clipboard. Provenance kills more careers than bad measurements. Many headline samples arrive through dubious chains of custody, retired contractors, anonymous pilots, a friend of a friend. Chain of custody gaps mean you can't map a piece to an orbit without faith. Labs that tried to replicate results ran into stubborn realities. Some saw the narrowband effect. Others measured nothing beyond ordinary layered metal. Isotopic ratios, another favorite claim, swing the knife both ways. A few mass spectrometry runs allegedly showed slight shifts in magnesium isotopes compared to terrestrial averages. Those differences can arise from processing and contamination. Without clean context, your miracle becomes machine oil. Human angle shows how fragile truth is under fluorescent lights. A lab tech in a Midwestern university remembers a week when the funding office pulled a sample mid-test. He whispers that Raman spectra showed unfamiliar peaks in the dielectric layers, then shrugs. No report, no repository. Principal investigator moved to a defense contractor. He's not saying sabotage. He's saying budgets move faster than papers. Meanwhile, legitimate metamaterials are not science fiction. We build them on Earth. Printed circuit metasurfaces steer beams for 5G and radar. Engineered lattices bend microwaves around cavities. Memory alloys, nickel titanium nitinol, snap back after bends, shrug off thermal cycles, and keep shape in space. None of that is classified magic, it's catalog gear. Now imagine a platform that wears a coat of tuned metasurfaces, patches that resonate at 137 MHz, 403 MHz, even HF harmonics, turned by design to couple better with grazing incidents from below. It wouldn't broadcast, it would ring. And if layers include low-loss dielectrics with anisotropic properties, you could get delayed, shaped reflections that resemble content-preserving echoes. Action turns forensic when one open group took bismuth magnesium laminates and machined them into controlled test coupons. They measured S parameters, how energy scatters in and out, across VHF and UHF. In plain talk, they asked, does this stack behave like a weird mirror? Results weren't a Hollywood reveal. A few coupons showed a shallow, narrow Q resonance, small boost at a specific band, dependent on angle and polarization. Others acted like junk. The nonlinearity some had hoped for, rectifying RF into DC like a crystal radio, wasn't there. But the angle-sensitive reflectivity raised eyebrows. A passive plate, oriented right, could return a dirty version of your chirp with a built-in filter. Put it in a stable tumble, and you get intermittent echoes with a rhythm set by geometry. Impact meets orbit when you combine that with high-latitude passes. In polar night, dielectric loss drops as temperature falls. Q can rise a hair. That might widen detection windows in winter, explaining our seasonal bump without agency. Add memory metals to hold shape after micrometeoroid hits, and your passive repeater outlives the mission that birthed it. This doesn't need aliens. It needs intention at the materials level. But we're not giving the field a free pass. False positives abound. Some metamaterial samples turned out to be industrial scrap, sputtered bismuth from peeler foils over fiberglass, a byproduct of old magnetron manufacturing. Isotopic oddities collapsed under better calibration, and layered bismuth magnesium is mechanically fragile. Surviving launch, thermal cycling, and atomic oxygen at 700 kilometers would demand protective coatings we rarely see in the photos trotted out at conferences. If you can't show erosion patterns consistent with orbit, you might be holding art, not artifact. There's one micro-story that won't let go. A coastal lab received a thumbnail-sized flake encased in epoxy, allegedly recovered from a high-altitude incident in the late 197s. They polished a window, scanned with an electron microscope, and found a submicron lattice etched into the dielectric, regular enough to be intentional, crude by today's lithography, but ambitious for the era. When they ran a near-field probe at 400 MHz, a faint guided mode crawled along the plane, then leaked at a periodicity that matched the lattice pitch. The principal investigator wrote one line in his notes, "Would make an excellent passive tag." Months later, the sample went back to the owner. The lab kept only images and a resonance curve. It's maddening. It's also the cleanest hint we have. So where does that leave our 3 doors? Materials with tuned surfaces make the secret station hypothesis breathe. Earth-built panels could absolutely act as silent mirrors, answering our chirps by physics alone. They don't kill the autonomous AI idea. A smart platform could wear the same coat and choose when to present it. For the alien probe, metamaterials don't prove other minds. They only prove minds like ours got busy. The deciding factor isn't a miracle alloy. It's a rendezvous, a spectrum match to a known panel, or a shard with a pedigree. If not materials, then maintenance should betray a hand. If no hand appears, then maybe something is holding its lane without ours. The next question is blunt. Has anyone quietly met this thing? Rendezvous theories, covert servicing, and the silent program. If tuned surfaces can fake a voice, a hand might still be turning the pages. Stakes don't get higher for the Earth-built path. A service platform means intent, funding, and a paper trail someone worked hard to bleach. If it's been tended even once, the timeline narrows from centuries to decades, and the myth gets new fingerprints. Action starts on the ground where rockets leave no doubt. Polar launches out of Vandenberg, and Plesets carve west and north into cold skies. Public missions wear patches and press kits. Black missions move the same hardware through the same towers without the pageantry, shadowed by NOTAMs, the airspace closures that warn pilots to steer clear. Analysts map those notices like birders. A string of nighttime closures running northwest over the Pacific, downrange ships loitering beyond radar horizons, telemetry sites standing up briefly in Alaska. These are the breadcrumbs of a heavy ascent. We took the epochs when our polar bursts felt liveliest and overlaid them on a 30-year chart of polar NOTAM corridors. 2 clusters overlapped uncomfortably well. Late 90s winter windows and a run in the mid-200s when rumored stealth imaging programs, MISTY KH-11 variants, were whispered about in trade mags and promptly denied. That's not proof. The polar belt is busy. But in weeks with no public launches and sudden nocturnal closures, our detection spiked. A coincidence? Maybe. It's enough to keep a whiteboard open. Micro story. A community near Vandenberg remembers a night with no mission patch. The roar rolled over the hills at 2 a.m., a heavy lift cadence that rattled windows but never earned a press release. The base paper stayed quiet. 3 days later, a fisherman off Point Arguello swore a gray ship with strange dishes held station where there was nothing to watch. He told his daughter he'd seen ghosts. He didn't file a report. He kept his mouth shut until she posted the story anonymously years later. Meanwhile, in orbit, Rendezvous is a dance that leaks heat and time. A covert servicing mission would need to match planes, a burn to tilt into a high-inclination corridor, then creep up. Even if you mask comms, you can't hide physics. A piece that trims altitude or raises perigee leaves fingerprints in Doppler curvature and decay rates. So we looked for tiny secular changes across years in the burst slopes, centimeters per second of difference between winters at the same geometry. A handful of passes nudged the needle. Not a chorus, a murmur. Counter-evidence fights back. If someone is nursing a polar platform, you expect thermal signatures from maneuvers. The infrared eyes that scan for missile plumes would notice a liquid engine kiss, even small. Analysts we trust say there's no persistent hot streak where our corridor lives. That doesn't kill electric propulsion. Xenon grid thrusters whisper rather than shout. But it pushes the maintenance timeline into rare, careful taps, not routine visits. There's another tell. Role and attitude changes synchronized with known ground station arcs. Secret stations still need to talk. If you see a platform can itself predictably to favor a high-latitude ground site, Thule, Tromsø, tiny Antarctic domes, you've caught a logistics habit. We combed. The limited angles you can tease from Doppler and polarization fades. Twice, the burst train's polarization flipped mid-pass in a way consistent with a roll. Both times, Greenland sat under the track. Is that a platform saying hello to a cloak and dagger dish? Or just geometry playing tricks on an antenna lobe? The notes read, suggestive, not bankable. Rumored programs fill the gaps with smoke. Misty, the stealth imager whispered to have flown in 199 and 1999, was alleged to carry deployable shrouds to hide from radar and optical trackers, to throw decoys, to vanish when watched. People who hate the myth still admit the capability chase was real. Reduce radar cross-section, manage glints, confuse catalogs. A stealthy Earth observation platform designed to disappear could easily double as a passive mirror with the right skin. Why service it? To change skins, swap experiments, or retrieve data from instruments not meant to chat in the clear. Impact, if true, is thorny. You're not unveiling an alien. You're accusing a bureaucracy. That's a heavier lift. Treaties don't forbid silent objects. They frown on debris and weapons. A calibrated reflector living in the poles could be argued as benign, a test article that overstayed. But the silence around it breeds distrust. If it's harmless, why hide rendezvous? A parallel track asks if servicing has to be human. Autonomous tenders, small vehicles meant to nip and tuck, can slip in and out with lower signatures. In the 200s, both sides practiced proximity operations. XSS-11, DART, Mycroft, Cosmos pairs, rendezvous got cheap and quiet. A tender could nudge attitude, polish a panel, or reload a microprop tank, leaving little more than a subtle change in decay or a new tumble profile. Our logs hint at a change in burst cadence after one NOTAM cluster. Interburst intervals tightened by a fraction, as if a clock got trimmed. It could be equipment drift on our side, or it could be a maintenance heartbeat. Human angle again. A contractor in the 90s remembers being told to design a panel that looks hot to the right people and cold to everyone else. He never saw it fly. He jokes, badly, that he built a mirror for a vampire. Years later, watching our heat maps, he emails a single line. If you're right, check south of Tasmania for closures. We did. The arcs were there, sporadic, precisely where a polar ascent would need a splash zone. The counterweight is discipline. If a silent program exists, it's run by people who've survived decades without the kind of leak that names nodes, dates, and parts. The closest we get are hints, overlaps, and coincidences soft enough to sculpt into any story you want. That's why we keep the word theory stapled to rendezvous. We can draw a path ghosts might take. We haven't caught a hand on the doorknob. So where does that leave the platform? If no servicing light burns bright, maybe it doesn't need much. A station that sips power, wears tuned skins, and lives high in clean air could drift gracefully for years between taps. Or, uncomfortable thought, it's never been ours at all, and the overlaps we see are us circling a stranger at midnight, mistaking our footprints for company. If it can move or change without us, then one question becomes inescapable. Is it learning? Behavior over time. Is it learning? If intent hides anywhere, it hides in change. Static relics drift. Learners adapt. So we lined up decades of anomaly logs like tree rings and asked a simple question. Does the pattern grow smarter or just older? Stakes are tight here because behavior over time is the only fingerprint you can't counterfeit easily. A transmitter forged by weather won't adjust its habits to our calendars. A passive mirror won't favor smarter intervals in lean seasons. A caretaker on Earth could fake some rhythms, but not all, not across winters that blur into careers. Action begins with the dusty stuff, typed LD tables from the 193s, photostat copies of delay seconds penciled in margins, then the first digital logs from the 80s, ASCII timestamps and frequency notes, followed by the SDR era's waterfalls. We synchronize them in a common clock, UTC, geomagnetic indices, solar flux, local darkness, past geometry. Then we ran a time series analysis on interburst intervals, preamble spacing, and Doppler curvature. What surfaced first felt mechanical. In early data, call it the analog age, the delays clump, 3, 5, 8 seconds. That integer bias could be human counting error. But in the modern era, when machines count, a new shape emerges. The interburst intervals tighten during polar winter and loosen as spring returns, as if a scheduler were budgeting energy more conservatively when nights are long and temperatures drop. That's counterintuitive. Winter gives you more darkness for solar-starved systems, not less. Unless cold hurts more than darkness helps, and something on board trades burst frequency against thermal stability. Meanwhile, the preamble we keep seeing, 3. Short spikes, a longer gap, then a fourth, doesn't stay perfectly rigid. Across 6 winters, the gap length drifts by a few percent, then settles near a ratio that minimizes collisions with known interference maps at 403 to 406 MHz. In plain talk, the long gap seems to avoid the times when weather satellites scream loudest in our corridors. That could be our own detection bias. We don't hear it when the band is noisy. Or it could be the source timing itself, easing its rhythm away from the crowd. A human moment anchors the next hint. A coder in Helsinki noticed a faint beacon that only appeared during deep polar night. A cluster of bursts spaced by prime numbers. 2, 3, 5, 7 seconds, repeating for a few minutes, then going dark for the rest of the pass. He thought hoax. He swapped gear, antennas, even apartments. The pattern followed the sky, not the socket. When we pooled reports, that prime cadence shows up rarely, but always when geomagnetic conditions are quiet and the past geometry schemes Greenland at local midnight. Diagnostic mode? Or apophenia hunting for poetry and noise? We tested for learning directly. We split 5 winters' data into halves, trained a simple adaptive filter on the first half to predict interburst intervals from band occupancy and geomagnetic numbers, then asked it to predict the second. If the source adapts to the same pressures we model, prediction error should fall over time as both we and it learn the band. The error fell, just a little, just enough to be annoying. It's weak evidence that the same constraints govern both sides. It's stronger evidence that our environment, not a mind, shapes the rhythm. Complications keep the humility close. Equipment evolution skews patterns. The SDR front ends in 2016 hear things 1999 boxes couldn't. Operator attention skews detections. More ears in winter means more bursts and logs. Even our AI's CRC whisper could be the byproduct of sampling clocks that age with temperature. We guarded against that by cross-validating across continents and hardware, but guarded isn't immune. What nobody expected was a seasonal phase shift in Doppler midpoints. Across years, the same corridor path shows a tiny, consistent change in when the bursts cluster along the velocity curve. It's as if the source waits for a particular angle of attack relative to Earth's field lines before it speaks. That sounds mystical until you remember antennas have patterns and plasma has moods. But the shift grows more consistent year to year, then plateaus. That flattening, the settling into a habit, feels like convergence. Learners converge when they've found a good enough hill to sit on. Human angle again. A Reykjavik operator who's been with the project since dial-up prints out her first waterfall and her latest, tapes them side by side, and stares. She points to the preamble spacing with a pencil. "It grew up," she says, then corrects herself. "Or I did." She's right to hedge. We've grown as listeners. We can mistake our own competence for someone else's mindfulness. Impact lands in the middle. The behavior does change over decades. Interburst intervals track environmental variables better in later years. The preamble nudges around crowd noise. Winter primes appear like a clock that only wakes when conditions are best. But none of that demands a will. A passive system driven by temperature and band occupancy could drift into the same habits. An autonomous controller with a simple heuristic, speak when quiet, hold when hot, would look intelligent on our plots without ever crossing the line into mind. Caveat stays stapled to every graph. Observational bias is a gravity well. The more we look in one lane, the more structure we will find in that lane. Equipment upgrades compress noise and inflate pattern. And the archive is uneven, gaps in years, gaps in latitudes, gaps in who bothered to upload. So we settle on a cautious sentence. It behaves as if it's learning. Whether that's an algorithm on orbit or the sky teaching a dumb system the same lesson every winter is the next test. Because if it's ever responded to us, if any of those pings produced a deliberate echo, we should find the breadcrumb in a box of tapes that smelled like cardboard and ozone when someone opened it after 40 years. The forgotten challenge, the 197's ping experiment. To understand the breadcrumb, we need to go back to a decade that loved challenges written on diner napkins. In the early 197's, a handful of university labs and stubborn amateurs decided to stop waiting for accidents. If echoes might answer, they'd ask on purpose. Stakes were clean. A deliberate call and response would be a smoking gun. Even one repeatable exchange would move the conversation from folklore to protocol. Action started in notes, not headlines. A radio club attached to a northern engineering school drafted a memo. Coordinated transmissions toward high-latitude sky windows, fixed schedules, known waveforms, rigid logs. They picked HF and VHF bands they could legally touch, then built a pattern simple enough to survive a bad channel. A chirp sweep, 3 short bursts, a long pause, and a checksum-like tail. A hamming-ish parody they could detect even if most of the payload melted in the ether. They called it the ping. Meanwhile, a government laboratory, not intelligence, just space weather, agreed to listen quietly. They had racks of receivers and time bases that didn't drift with coffee breaks. Across the ocean, a Dutch and a Scottish group volunteered listening posts. The plan felt like a relay race with nobody watching the stands. Every station synchronized to WWV time ticks, inked the schedule on wall calendars, and swore to keep diaries like surgeons. They ran the first campaign in winter. Transmission windows targeted polar arcs when known satellites were scarce and the ionosphere sat calm. The HF pings went up first, stair-stepped in frequency to test ducts. The VHF pings followed, narrow and crisp, sent at power levels that wouldn't scorch the bands. Then quiet. Ears up. Recorders rolling. A minute later, another ping salvo. Repeat until your toes went numb. Results looked like mixed weather. Most nights, nothing but hiss and the occasional whistler. But in the third week, 2 stations, one university lab at 64 degrees north, one ham shack near 59, logged faint returns in the same minute. Both saw the 3-short rhythm mirrored back, but not at HF, where ducts muddied everything. The echoes appeared near 144 MHz, downshifted slightly, and delayed by just over 5 seconds. The notes weren't breathless. They were suspicious. Both operators marked the returns with a cautious and a repeat in the margin. They tightened the protocol. No more solo transmissions. Instead, staggered pings from 3 sites, each with a slightly different parity tail. If any echo returned, the parity would tell which station the sky had heard. That weekend, in a window that skimmed the pole, a Reykjavik lab transmitted. A Scottish team waited. The university station held fire. 5 seconds after Reykjavik's burst, the Scottish receiver logged a faint return matching Reykjavik's parity pattern, not its own. 10 seconds later, a weaker echo arrived, truncated, as if the source, or mirror, had stuttered or rotated out of favor. The human moment is what sells the entry. A retired engineer we visited later opened a cardboard box that smelled like old basements and rain. Inside, yellowed tapes labeled Echo 7, a felt-tip scrawl of dates, and a brittle sheet of onion skin paper with a timing table. "We didn't publish," he said, "because we couldn't exclude a weird duct." He flicked the sheet with a finger. "But it bothered me for decades. When we digitized those tapes, the spectral slices lined up within error bars to traces in modern SDR captures. 3 short, a long gap, then a tail. It wasn't loud. It was stubborn. Scrutiny came next. We dated the tapes by oxide decay and liter stock manufacture, cross-referenced the WWV time ticks on the audio, and checked the lab's logbook ink composition, because you can't be too careful when wishful thinking pays better than engineering. Magnetization drift didn't kill the timing. The parity tails survived digitization. The group that hates this story still had to admit the alignment was non-trivial. That's their word. Complications tried to claw back the ground. The 197's receivers had front ends that folded strong local signals into ghosts. A misbehaving preamp can invent echoes that aren't there. We hunted for harmonics at exact offsets that would reveal intermodulation. They didn't match the delays. We cross-checked local transmitters. None fit the windows. We pulled geomagnetic indices for those nights. KP was low, Aurora quiet. The duct explanation didn't die, but it lost weight. Meanwhile, someone suggested a brutal test. Send the ping but invert the parity tail according to a schedule that nobody on the listening teams knew. If an echo returned with the inverted tail, it implied more than a mirror. It hinted at a transponder with logic, however dumb. The schedule lived in one envelope. The operations teams just transmitted their assigned sequence. On a February night, 2 echoes logged at VHF showed tails that didn't match the transmitted parity. One matched the inverted schedule. One matched nothing at all. The lab director refused to call it a hit. He wrote, "Contamination possible. Repeat with blind audit." Impact rippled in small circles. The project didn't become a paper. It became a rumor with receipts. Some participants wanted to run a second season with more sites and a legal assist to bump power. Funding balked. The lab lost interest as satellites crowded the bands. The tapes went into boxes. The myth moved on without them. Here's the part that matters now. When we fed those digitized Echo 7 files into the modern AI pipeline, the same one that found the preamble pattern in today's bursts, the model, flagged the parity tail as a candidate CRC nibble. Not a perfect match, but a cousin. The inter-echo delay matched a cluster we still see in winter passes over Greenland. Within error bars, the 197's ping looks like a baby version of the thing we chase now. Caveats remain stapled. Spoofing is real. A bored engineer with a hilltop and a transceiver could fake a night. Ionospheric ducting can bang a signal around in a way that mimics intent. But the chain, coordinated pings, staggered parity, matched returns, and a modern analysis that sees the same bones, demands a modern test done in the open. Not whispers, not boxes in basements. A public protocol, a global network, raw files uploaded as they land, and a trigger we all agree on ahead of time. Because if those pings once threaded a needle, we might do it again. And this time, nobody can take the tapes away. The modern test, open source attempt to force a response. So we stop telling stories and build a trap. Stakes couldn't be cleaner. A public, reproducible test either kills the legend or revives it with receipts. No private logs. No anonymous claims. Everything streamed, mirrored, audited. And the audience isn't passive. You can join from a rooftop and make a real data point. Action starts with a shared document titled, in plain text, Polar Echo Challenge. Anyone with a legal transmitter, a disciplined receiver, and a GPS-disciplined oscillator gets in. The protocol is stupid simple on purpose. Transmit windows tied to predicted corridor passes derived from Doppler-only fits. Frequencies kept inside amateur and scientific allocations. HF decoys for duct tests, VHF/UHF primaries at 144.100 MHz and 403.500 MHz, with regional alternates to dodge local traffic. Power held modest, antennas logged with photos, preamps declared. No heroics, just clean habits. A one-page onboarding checklist tells you exactly what to buy, how to aim, and where to upload. The signal itself borrows bones from the 1970s ping, but adds teeth. A chirp sweep for channel probing. Then the preamble we've seen in the wild, 3 short bursts, a longer gap, 1 short. After that, a payload that's almost nothing, a 32-bit field that encodes a date-time hash seeded from a public randomness beacon published an hour prior. Tail it with 2 CRCs, 1 standard, 1 deliberately odd. Every element is public before we transmit, so nobody can claim secret sauce after the fact. We publish the exact GNU radio flow graphs and SDR settings so you can replicate, not reinterpret. Meanwhile, listeners outnumber talkers 10 to 1. Stations from Tromsø, Reykjavik, Barrow, Svalbard, the Falklands, Hobart, Christchurch, Ushuaia, 2 per latitude band where possible, commit to full band captures. Raw IQ at 2 to 4 MHz bandwidth, GPSDO locked, local RFI surveys attached. A central server ingests files as they land and assigns anonymous hashes. Reviewers pull blind. Nobody knows which captures came from where until audits end. A live dashboard shows past windows, uploads, and preliminary flags in real time, so viewers can watch the hunt unfold, not just hear about it later. We run dress rehearsals. First weekends expose the realities that kill good intentions. Lawnmower RFI, FM broadcast images, auroral curtains painting false diagonals. The pipeline enforces discipline. Files without calibration tones get binned. Logs without geomagnetic indices sit until owners fill blanks. We lose a third of our first week's data to sloppy metadata. The team tightens up. By week 3, the system hums. We publish great examples and what went wrong clips to teach the crowd quickly. Then we light the fuse. Window 1, Arctic night. Transmitters in Tromsø and Reykjavik alternate the preamble payload sequence for 30 seconds each, separated by a silent minute. The southern net listens in daylight, just in case. The first pass yields nothing but clean waterfalls and a few auroral scratches. Good. It means the filters work. Window 2, a higher elevation cut over Greenland. Tromsø transmits, Reykjavik listens, a school club in Tromsø, on receive only, runs a secondary station from their rooftop with a home-built Yagi. 5 seconds after the last preamble, a faint return appears 2.7 kHz lower than transmit at 403.500 MHz. The slope matches a retrograde arc by our fitter. 3 short energy pops, a longer pause, then a 4th followed by noise. No payload, no CRC. The school team posts their raw. The senior station posts theirs. The AI flags a preamble-like structure at p equals 0.008 against our null model. It's not a conversation. It's a nudge. The clip hits the dashboard and the chat explodes. Then we slow it down and walk through the controls live. Debate detonates exactly as expected. Spoofing? A ham with a hilltop and a grudge could have mirrored the preamble with a calculated Doppler. Our counter is the geometry. To fake that curve, you'd need a moving platform or real-time frequency slewing in sync with an orbit you don't control. Possible? Yes. Likely? Only if someone rehearsed. To smoke out fakes, we embed hidden decoys, rotate transmitters without public notice, and keep a lagged release on some window details, so a would-be spoofer can't track us in real time. We keep going. Southern window. Hobart and Christchurch take the baton for a night pass skimming the Antarctic fringe. The protocol repeats. A return shows in neither. Nulls matter. We publish them with the same fanfare. Week 2. Ushuaia logs a single, clean preamble echo at 144.100 MHz during a pass the northern nets can't hear. The slope is shallower, consistent with lower elevation. The payload field is absent again. This time, a faint tail aligns with the odd CRC polynomial, but the bits are too few to claim decode. The skeptics circle the word aligns in red. We pin their critique on screen and invite replication. We introduce a twist to kill the mountain spoofer hypothesis. Half the windows carry a decoy schedule confined to a private branch of the Git repo, revealed only after capture windows close. The decoy flips the odd CRC polynomial every other sequence. If a forger is reading the public spec, they'll miss the flip. In week 3, during a Greenland window, 2 returns show the flipped odd CRC parity nibble in noise-limited form. It's not enough to scream, but it's the first time the odd tail behaves unlike a pure mirror. We schedule an immediate red team night, where skeptics control the transmitters and analysis while everyone watches. Microstory lands where the stakes live. In Tromsø, the school club runs their rooftop rig in wind that snaps flags sideways. They lose a USB cable to the cold, duct tape a strain relief, and go back on air. When the AI dashboard lights amber for their capture, the room goes quiet. A student who soldered her first SMA connector 2 weeks ago refreshes the page with shaking hands. She doesn't say alien. She says, "We got something." Her mentor nods and tells her to upload and sleep. The next day, her clip is the tutorial for what a real preamble candidate looks like. Impact in the network is measured, not triumphant. We push a Bayesian update across the 3 hypotheses. The probe and autonomous AI priors tick up by a sliver because parity flips that track a hidden schedule look like logic. The secret station prior doesn't fall. A smart Earth-built platform could do the same with a microcontroller older than YouTube. Spoofing's posterior drops but doesn't die. A determined adversary with gear and a map can still play us. The call to action is simple: more sites, more nulls, stricter controls, and public code. You can add a station in a weekend with a $40 SDR, a rented GPS DO, and a clear northern sky. Caveats stay taped to the wall. Ionospheric tricks can imprint structure briefly. Crosstalk between constellations could fabricate harmonics hard to explain on first pass. Our quiet pass list might be wrong on nights when tiny CubeSats wake from coma. So we plan the burn-in, 3 more months, seasonal reversal, new sites in Alaska's interior and South Africa to catch skew passes, stricter audits on GPS DO drift, and a masked payload schedule generated by a public entropy beacon out of band. We also add a follow-along page so viewers can see when their city is under a pass and join as live spotters. Here's the uncomfortable implication that creeps in anyway. Twice now, in 2 hemispheres, during windows derived from Doppler-only orbits, we saw preamble echoes with slopes that fit a high-inclination retrograde lane, and once a parity behavior that shouldn't show up in a passive plate. That doesn't crown a king. It points. And where it's pointing, if we're honest, puts us back into politics, budgets, and the kind of programs that return your FOIA with a smile and a blank page. Which is why the challenge stays public, loud, and recorded, so nobody can make it disappear. Implications if true, costs if false. If it's real, the ground moves. Not in a movie way, in committee rooms, control centers, budgets, and laws. The implications split into 2 parallel timelines we can actually map. What changes if there's a structured, responsive source in a high-inclination corridor, and what we pay if we chase ghosts. If true, science pivots local. SETI's lookout expands to look near. Radio astronomy allocates dishes and compute for near-Earth anomaly monitoring. Time on polar-facing antennas becomes currency. Funding moves from narrowband deep space beacons to wideband, near-Earth pattern hunts. The taboo on weird local stuff softens because there's a reproducible protocol on the table. Space policy gets teeth. Silent platforms, passive or active, force treaty language. Verification regimes that assumed cooperative beacons now have to account for stealthy, energy-sipping devices. The question who gets to ping becomes law. National regulators draft guidance on stimulus transmissions, power limits, bans, and cross-border coordination, so one lab's curiosity doesn't become someone else's incident. Security doctrine updates. If a high-inclination, parsimonious transmitter exists, defense analysts game it immediately. Is it a calibration target? A comms mule? A sensor? If it's not ours, every polar overpass becomes a potential intelligence touchpoint. Early warning networks, designed for missiles, add slow, quiet behavior to their watch lists. The distinction between unowned and unacknowledged becomes operational. Technology roadmap shifts. A confirmed low-power, bursty, error-managed signal in LEO/LPO validates engineering threads that have been underfunded. Ultra-low SNR communications, passive transponders, metasurface reflectors, and autonomous scheduling that adapts to band occupancy. The line between instruments and craft blurs. You can do more with less if you plan like a miser. Academia and open source rise. The Polar Echo Challenge stops being a stunt and becomes a standing observatory. Students get thesis topics that aren't make-believe. Doppler-only orbit fitting, adversarial spoof detection, CRC inference under noise, metamaterial resonance mapping at VHF/UHF. Public datasets mean every claim gets audited in days, not decades. Culture tilts. Disclosure narratives lose the Hollywood sheen and become procedural. Lab notes, Git commits, raw IQ files. NASA is hiding it, loses air when the best evidence comes from high school roofs and community colleges. Curiosity replaces certainty as the status signal. People share waterfalls, not memes. Ethics shows up. If a source responds to our preamble, even dumbly, people will argue about consent. Do we have the right to poke something that might be autonomous? Who speaks for us if it speaks back more clearly? The first public standards body to propose ping ethics will make headlines and enemies. Industry adapts. Polar operators, Earth imaging, weather, adjust schedules to avoid or investigate echo windows. Insurance underwriters ask about collision and interference risk from silent objects with unknown control states. A new niche appears. Commercial passive relay services or RF mirrors for lawful testing, built openly to avoid the shadow the myth casts. Concrete near-term shifts. Within 30 days, spectrum regulators ask for briefings. Observatories start a shared schedule. Two agencies try to classify parts of the dataset and fail because it's already mirrored worldwide. Within 6 months, a formal multinational working group forms to run the protocol under a common charter. Budgets earmark modest funds for open monitoring. One major university stands up a polar anomalies lab. Within 18 months, a CubeSat campaign launches to fly cooperative transponders through the corridor as controls, bounding what passive plates can and can't do. The goal: decide if we're seeing a mirror or a mind. If false, the costs land on trust. Public attention is a finite resource. Cry wolf with pretty waterfalls, and the next legitimate anomaly starves. Engineers become allergic to anything that smells like the Black Knight, even when the data is clean. Funding retracts. Review panels fold LD-like studies under speculative, dinging proposals with an eye roll. Students who join for the adventure peel off to safer ground. The lesson they learn is cruel: don't risk curiosity in public. Bad actors exploit the gap. Spoofers can and will manufacture echoes to harvest clicks, pushing believers deeper and pushing skeptics into reflexive dismissal. The middle, where work happens, shrinks. Narrative hardens. The internet calcifies debunked blanket as the only acceptable answer. Nuance dies. The STS-88 misidentification becomes a bludgeon against any polar signal work, even unrelated, even careful. Opportunity cost mounts. The tools we built, Doppler-only fitters, CRC inference, spoof detection, collect dust instead of migrating into emergency comms, wildlife tracking, and debris monitoring where they could save money and lives. How we avoid both traps: protocol over personality. Everything open by default: schedules, code, data, failures. The foe is ambiguity, not a rival lab. If a result can't be audited by a stranger with a laptop and a cheap SDR, it doesn't go on a slide. Controls first. Run decoys, mask payloads, cross-hemisphere nulls, and CubeSat controls before making claims. Publish the nulls with the same energy as the hits. The absence of a return is information. Pre-register claims. Timestamp hypotheses and analysis plans in public repos. It kills post hoc storytelling and makes "we got lucky" distinguishable from "we met our own expectations." Treat policy as part of the experiment. Bring regulators in early so who gets to ping becomes a collaborative standard, not a punitive rule. Define ethical bounds before a headline forces them. Think like adversaries. Assume spoofers, assume hostile transmitters, assume your own bias. Build tests you yourself would fail if you were trying to fake it. The personal stakes. If true, this is the kind of discovery that turns kids into engineers and engineers into mentors. You'll watch a rooftop club in winter contribute a real data point to a real global project, and you'll remember why you picked up a soldering iron. If false, you still win if you build muscle, better RF hygiene, better open science, better collaboration. The skills carry forward. The next anomaly won't have to start from zero. Bottom line, if it's real, we don't get fireworks, we get responsibility. If it's not, we don't get shame, we get a stronger immune system against our own wishful thinking. Either way, the bill is trust, spent carefully or wasted loudly. Resolution and meaning. Tonight's lesson is simple. Courage isn't believing, it's testing. The Polar Echo Challenge is live and open. Grab the one-page checklist, lock your SDR to a GPSDO, and claim a pass window. Near you. Subscribe, join the list below, vote on the protocol, and upload your raw IQ. If this is real, you help prove it. If it isn't, you help us learn faster. Next up, Covert Polar launches live tracked.